Hello, everybody. This is our group project, and it's over Newton's first law of motion. To introduce myself, I'm Jasmine Cooper. My major is health science. And to start off, we're going to start off with what is Newton's first law. So, Newton's first law can be described as a body at rest remains at rest, or if in motion, remains at motion at a constant velocity unless acted upon by an external force. This can also be known as the law of inertia. Scientist Isaac Newton's observation that objects at rest stay at rest highlights the idea that objects maintain their current state of rest, of motion, unless acted on by an external force. This can also be the same for objects in motion. If an object is in motion, it stays at the same speed or velocity unless an external force changes that. This basically means like your car is going to stay at its constant speed unless you press further down on the gas or unless you press on the brakes. The brakes and the gas can be described as your external forces. So relevant fields would be force. Force plays a crucial role in Newton's first law because it is the external influence that causes the change in velocity and motion. Inertia is the tendency of an object to resist change in its state of motion. Mass affects how much force is needed to change an object's motion or velocity. Objects with higher mass have more inertia, requiring more force. Direction of the external force can influence motion depending on where the force is applied to an object. An example of that could be tennis. You want the ball to be hit at a certain point, you hit it at an angle. By understanding the law of inertia, we can deeply understand how objects act independently without forces acting upon them and with forces acting upon them. Relevant scientists that were involved in Newton's first law include Galileo. Galileo was the first one to formulate the law on inertia. He was also involved in many other discoveries that influenced other scientists, such as relationship between distance and time, acceleration, and the parabola path of projection. The concept of inertia was later brought in by René Descartes before being developed by Isaac Newton. Here are some pictures of the scientists.
Hello, I'm Irena Roberts, and I'll be doing the second section to Newton's first law. The original experiment process. Galileo was one of the first to challenge the Aristotelian idea that a force is needed to keep an object in motion. He conducted a set of experiments using an inclined planes to study motion and inertia. Setup: Galileo rolled balls down smooth inclined planes to reduce the effects of friction. He also observed that the balls sped up as they went down and slowed down as they were going up. Then he connected two inclined planes facing each other, letting a ball roll down one side and up the other. The observations were when the second ramp was steep, the ball would climb early to the same height from which it started. When the second ramp was more shallow, the ball would travel longer distance to reach the same height. When the second plane was laid flat, which is horizontal, the ball kept rolling for a much longer distance without coming to an immediate stop. The conclusion: the ball would continue to move indefinitely on flat surface with no friction or resistance if that was present. This led Galileo to propose the idea of inertia, which Newton later refined into his first law. So while Newton stated the law clearly, it was Galileo's experiments and logical deductions that provided the experimental foundation for it. Newton's genius was in generalizing. The difficulties and complications. A problem. In everyday life, object in motion usually slow down and stop, contradicting the idea that motion continues unless acted upon. Another problem, Newton's first law only holds true in what's called inertial frame of reference, one that is not accelerating. The motivation for Newton's first law came from a desire to understand what causes motion and, more importantly, what happens when no force is acting. This was a major shift away from the ancient views, especially Aristotle's, which claimed that an object would only stay in motion if something kept pushing it. The original beliefs of Newton's first law were both scientific and philosophical, helping reshape how people thought about the universe. When Newton's first law was introduced in the Principia Mathematics in 1687, the law offered several groundbreaking advantages.
So for the modern experiment, I chose to do just a simple one that could be with objects found around the house. So you're going to need a toy car, a smooth surface, and a notebook if you would like to record your findings. So the procedure is you place your toy car on a flat surface, gently push your toy car. You don't need to do too much with the toy car, like relax. Observe the toy car until it stops, and you could record when the toy car stops. Recording means like you can place a marker where it stopped when you pushed it this hard, another marker where you pushed it a little bit harder. Outcome of the experiment. While observing the toy car gliding down a smooth surface, there are some key factors to remember when doing this experiment. So the smooth surface has no friction, therefore allowing the car to maintain the same speed. If you were to try and push a toy car on carpet, it's not going to work. The car will eventually stop. When it does, it will stay stopped unless you push it again. These key factors allows this experiment to be a perfect example of demonstrating Newton's first law and showcasing inertia. So the differences in the modern experiment rather than the original experiment is that the modern experiment highlights that if nothing is stopping the car, then the car will keep moving. Also, that when it stops, it will stay stopped. In the original experiment, the ball's velocity is manipulated by ramps and incline planes. The observation in the original experiment were that the ball will lose speed when going up a steep incline, whereas the modern experiment highlights that nothing's stopping the ball, that if nothing stops the ball, it will continue to, if nothing is stopping the car, it will continue to move unless acted on by a different force. Okay, the benefits of the modern discoveries. The modern benefits of the laws of inertia apply to our everyday life. As an example of this is when you strap your seatbelt in a car. When driving, as you come to a stop, you may notice that your body wants to keep moving forward. The seatbelt prevents your body from moving forward. This is a prime example of an external force to stop momentum. By using laws of inertia, we know that seatbelts are a necessity in order to prevent injury in car crashes. Your seatbelt is going to stop your body from flying through the windshield. Let's always buckle up. Okay, future expectations of research discussed. The future expectations of Newton's first law is that we can expect more changes in commercial flight planes. With technological advances in flight systems and engines, we can expect planes to reach new speeds a safe way. We can go from California to across the country in maybe 2 hours, hopefully. Thank God. With these new speeds achieved, we will need to use the laws of inertia to maintain a constant speed and also take into account external forces such as weather, gravity, atmosphere, and temperature. These external forces, we're going to need something to keep us stable while flying, which we already do a good job, but if we're moving at faster speeds, things are going to get a little bit more complicated. And that's...
Okay, so For our example question, we have a book is lying on the table. It stays at rest until somebody pushes it. Which of the following best explains why the book doesn't move on its own? So you have A, there is no net force acting on it. B, the force of gravity is pulling it down. C, the book is too heavy to move. And D, the book has no energy. So in this question, your answer would be A. And for our extra choice, E, we have the table applies a force that keeps it in place due to friction. So our example question relevance, this question is relevant to Newton's first law because it's all about an object staying at rest until net force acts on it. Newton's first law, aka the law of inertia, says an object at rest stays at rest, and an object in motion stays in motion at constant velocity, unless acted upon by an unbalanced force. So when the book just sits there, not moving, it's a perfect example of inertia. The book wants to stay at rest, and it does, because nothing's pushing or pulling it in one direction than another. So no net force equals no change in motion. And the benefits of understanding the question given is that one, it helps you recognize real world examples and you start to notice that objects only move or stop moving because of forces. Two, it builds your intuition about forces. You get better at spotting when forces are balanced versus when they are unbalanced. And three, it clears up any common misconceptions. So once something's moving, it'll keep moving and going unless something stops it. For example, a friction or a wall or anything. And four, it can prep you for more complex physics. Newton's first law is the foundation for understanding acceleration, momentum, and Newton's second law. And the process of writing the question. So number one, you have to identify the core concept, which is the heart of Newton's first law, which is an object stays at rest or in motion unless the net force acts on it. Two, you have to choose a simple and relatable example. So I picked a book on the table because it is easy to visualize, it is familiar and not moving. So it's perfect for the at-rest part of the law. And number three, you have to write a clear question stem. So I made the question ask, why doesn't the book move on its own? And that directly leads the student or anybody who's reading it to think about forces and motion. And four, you have to create the answer choices. And the correct answer is one that clearly reflects Newton's first law. And the distractors, one based on the true fact, one with a misconception, and one that sounds scientific but is off topic. And the uniqueness of the question is that it targets a specific misunderstanding because instead of just asking, what is Newton's first law? It makes you apply the law to a real world situation, which is why the book stays at risk. And that challenges people to think who think they understand it, but still believe that things need a force just to stay still or stay moving. And the wrong choices are realistic misconceptions. It's too heavy to move. Well, weight does not equal motion. Gravity is pulling it down, yes, but it's balanced. And they're not silly, they sound right, which makes the question actually test understanding. And it sets you up for deeper learning because you can use this one question to talk about balance versus unbalanced forces, introduce inertia, and lead into Newton's second law. So it's simple, but it opens the door a lot for the reader. And demonstration or solving. So you have, for your materials, you have a book, a flat surface like a table, and your finger. So step one, place a book on the table and it stays still. Number two, don't touch it. It stays still forever, in theory at least. And three, gently push the book and it's gonna move. So number four, stop pushing and friction is gonna slow it down. And what you see is at rest, stays at rest. No unbalanced force. Moves because of an unbalanced force, which is your finger. And it stops due to friction, which is another unbalanced force. And these are just some relevant charts, graphs, and diagrams. You have force of gravity, normal force, inertia, good stuff. And any relevant formulas or constants that are described. So you have Newton's first law, which is F equals D times P divided by D times T. You have normal force, which is Fn equals F times G. And weight, which is force of gravity, you have Fg equals M times G. And for net force, you have F net equals M times A. And for constants, you have G, which is acceleration due to gravity. The value of G is 9.8, and the unit is m/s squared. And then F is force, and the unit for that one is newtons. M is mass, the unit is kilograms. So the solving process thoroughly described. To solve a Newton's first law problem, you have to identify all forces acting on the object and check if they are balanced. And if the net force is zero, like gravity, and the normal force canceling each other, then the object stays at rest or moves at constant velocity. So no change in motion happens unless an unbalanced force is applied. And the solution correct or applicable to the topic is a correct solution for a Newton's first law problem will be recognizing that a book resting on the table stays at rest because the forces acting on it, which is gravity downward and the table's normal force upward, are equal and opposite, resulting in a net force of zero. And since there are no unbalanced forces, the book does not move, which perfectly applies Newton's first law of motion. That's it.
My name is Emily Flores, and I was in charge of section 6 in the Newton's first law project. Please not take off points for my Minecraft background. Just thought it was pretty cool. Okay, let's get started. 6.1 Additional information. Newton's first law of motion, which is also known as the law of inertia, it is how motion works in the real world. Inertia is everywhere. It is what causes you to jerk backwards when your car suddenly stops. Isaac Newton also discovered calculus, which he called the method of fluxions. He also wrote books about his works in the history of science, which is where he introduced the law of universal gravitation and formulated the 3 laws of motion. Newton worked together with many different scientists, including John Flamsteed. Newton persuaded Flamsteed to give him some of his observations of the moon, but he later published some of his work without giving credit. Newton was only 23 years old when he developed the law of motion. He presented the laws in his book that he wrote called Principia Mathematica in 1687. Newton also used Galileo's idea of inertia as the foundation for Newton's first law. 6.2 Additional interests. Newton's law would become clearly true if we imagined a place with no friction, like space for example. But because we live on Earth and not space, it took centuries to realize that stopping is caused by hidden forces. Many laws in science describe what happens when forces act on one another, but for Newton's first law, it showed what happens when no forces act. Aristotle believed that an object required force to be able to stay in motion. Newton's first law overturned that. You might expect that objects move until something stops them, but no force is needed to keep something moving. Okay, 6.2.1. We tend to think that motion needs effort, but Newton has proven that motion is standard if nothing is there to stop it. The first law describes inertia, but it does not describe what causes inertia. Although the first law gives you motion and forces, you still often wish the law said how motion would be in a real-world environment. If we had more time, we would study the origin of inertia and ask questions like why do objects resist changes in motion? Another topic I'd like to know more about would be Kepler's law of planetary motion, and Newton's law explained why Kepler's law worked. 6.3 summary. At the beginning, this project was very overwhelming and stressful. I can say me and my group were a bit confused on the format of the project and the recording of the progress of the project as well. But after talking it out, we had a better understanding and we were all able to get it done. The most important part of this topic would have to be the concept of inertia and to think about how people believed motion required a force. Newton showed that change in motion required a force instead of motion itself. The importance of this project is to be able to have a better understanding about Newton's first law in a way where we can explain it in a more detailed way. 6.4, these are our sources, and then one more slide up of our sources. That is it.